Welcome to my video. Today we want to look at the concepts in linear programming, special concepts in linear programming. And these concepts are the slacks, the surpluses, and the shadow prices. And we want to look at the differences between these concepts and how we can actually compute them in a linear programming problem. So we begin looking at, first of all, the slack and the surplus variables. And these are usually additional variables that are usually added to any linear programming problem, particularly the constraints, to make them as equations. We have already known in the past that a linear programming, a model always consists of the objective function and as well as the constraints. But then these constraints are in most cases are inequalities. So these inequalities can actually be converted or transformed into equations or equalities by adding, subtracting a variable on the left-hand side of the constraint to make it an equation. So a slack variable is now that variable that is added the constraint, particularly the constraint that has the inequality sign of less than or equal to. So as to convert it into an equation or an equality. And what this means maybe in economic terms is that, remember this, most of these constraints are usually the resource constraints. And so when we add them, it means the slack variables here represent the unused resources. The unused resources in the form of time or money and so on. And so you're talking of having achieved the optimal solution, but then some resource constraints have been underutilized. And so the level of underutilization is what we are calling now a slack variable in this case. On the other hand, a surplus variable is one that is usually subtracted from a constraint of the type greater or equal to, of course, again, with the same intention of converting it into an equation. And so what this really means now in the context of linear programming or economic terms is that a surplus variable actually represents over-fulfillment of the requirement, actually from the word surpassing. So you are required maybe as a constraint, maybe your condition was to maybe produce maybe 30 products, but then you have gone ahead and produced 50. So that means you have not only fulfilled or met the requirement at optimal, but you have also surpassed by, in this case, 20 more units. So the 20 will now be a surplus. It's an over-fulfillment, surpassing the requirement. And then the binding constraint, these are constraints with zero slack or zero surplus. In most cases, we shall be representing these slacks and surplus variables using letter S. And so if you calculate and you're finding that a particular constraint has a slack associated to it or a surplus associated to it equal to 0, then that is not just a resource constraint, but it's also called a binding constraint. And in most cases, actually in all cases, all binding constraints always pass through the optimal point. If you have graphically drawn all the constraints or graphed all the constraints on a linear programming problem, you'll find that the optimal point in the feasible region is a point where all the binding constraints actually intersect. And so binding constraints always have zero slacks or have no surplus at all. Before we are able to now begin at looking at how we can calculate the slack variables and and the surplus variables and probably identify a binding constraint, we have to learn how to express a linear programming problem in standard form, which is just more of a continuation of what we have just mentioned. Because standard form of a linear programming problem makes use of conversion of inequalities into equations. So when you're able to do that, then we say that the problem has been expressed in standard form. Now, one thing you have to mention is that we have said there are various ways of solving linear programming problems, but what we have discussed so far is a graphical technique. But the other techniques in the literature, like the simplex method for solving linear programming problems. So when you get deeper into the simplex technique, you realize that the simplex technique requires that one of the preliminary stages is to convert the formulated linear programming problem into standard form before you can proceed. And so for us, we are just learning here to convert it into standard form for the sake of calculating the slacks and the surplus variables. But we are not going to get into the details of simplex and how we can also use simplex technique to solve a linear programming problem, particularly with more than 2 decision variables. So just like you have said, expressing a linear programming model into standard form involves having constraints which are naturally in the form of inequalities converted into equations. And this can be done either by adding or subtracting an additional variable, which could be a slack or a surplus. So we have said that if we add, if the variable is added, then it's a slack. And if the variable is subtracted, then it's actually a surplus variable. And so the guidance is actually, the distinction comes in when you look at the nature of the inequality side that is actually used in that particular constraint. Maybe look at a case, typical example of a linear programming problem and see how we can use it to compute those terminologies or those quantities. Now, if we have a case example here that talks of a plant that is so much engaged in producing fluorescent tubes and energy-saving bulbs, so those are the two products. Once they have made the products, they are able to sell each bulb at 60 shillings and each tube at 60 shillings and each bulb at 80 shillings. And so the manager of the farm or the plant wants to determine the daily production plan that will actually maximize the contribution to sales revenue. And so the intention of the manager is to increase or get the highest sales from the two products as much as they can. So the entire of this narrative is summarized in a table form where we have a number of resource constraints here: the labor hours, the machine hours, the glass material, the coating material, against the products where we are talking of the fluorescent tubes and the energy-saving bulbs. Those are the two products. And the labor hours available, probably these are labor hours provided by the human resource. A maximum available is 900 hours. Machine hours, we have 1,200. Glass material, we have 4,500. And the coating material, we have 200. And this could be in quantities different, maybe in quantities of kg and so on. So we see that for one fluorescent tube, it requires 3 labor hours, 5 machine hours, a material size of glass about 25, and 1 coating material for 1 fluorescent tube to be ready. While an energy-saving bulb requires 5 labor hours, 4 machine hours, and glass material 18, and 1 coating material. And so from this, we need now to formulate a linear programming problem. But before that, there's an additional constraint. We are told the Ministry of Energy has issued a directive that a minimum of 40 bulbs must be produced per day, and this is in conformity with the energy saving strategy. And so this is an additional resource constraint. So we need to formulate the linear programming model. And for us to do that, of course, we have to do some coding here by letting X1 to represent, let's say, the number of fluorescent tubes that have to be produced and sold, and X2 to represent the number of energy-saving bulbs, so that then we can be able to formulate the objective function as well as the constraints that form the linear programming model. So when we do that, we shall be talking of if a fluorescent tube is to be sold at 60 shillings and an energy-saving bulb at 80 shillings, then it means the objective function is one of maximization kind, which will actually be in that particular form, 60x1 plus 80x2. But we are saying this is subject to some constraints, and one of the constraints has to do with the labor hours, which I have said is 3x1 plus 5x2. That will give you the total labor hours for the two products. But then we have 900 labor hours available. And then the second constraint now has to do with now the machine hours, which I have said that this will be 5x1 plus 4x2. This should also be less or equal to 1200. And then you'll have the glass material, 25x1 plus 18x2. This should also be less or equal to 4500. Then you'll have a resource constraint to do with the coating material. We have seen each product requires just one item. So this should be less than the 200 available. And then we have the ministry directive, which requires that the energy saving bulbs must be at least 40 per day. So this is the objective function, and these are the resource constraints. You can also add the non-negative constraints where you say X1 must be non-negative and X2 has also been a negative. But once you have one of the resource constraints talking of X2 greater than or equal to 40, it is almost needless to write this X2 greater or equal to 0. However, there's no harm. So once you have managed to plot this to formulate, you can now graph all these constraints, then help you find the optimal solution. So when you graph, you should be able to get the optimum point being x1 equals to 50 and x2 equals to 150, so that we can actually get that maximum sales by substituting x1 50 and x2 being 150 to get the maximum sales possible. Although the intention of this video is not to help us solve a linear programming graphically, because we have seen that before. We want to now see, once you have gotten this solution, how does it relate to what we want to discuss today on slacks, surpluses, and shadow prices. So the next quiz now requires us to rewrite the linear programming model that we have formulated in standard form. So rewriting this inequality in standard form, first of all, this is the linear programming problem that we want to formulate now in standard form. So we can call this as the ordinary version of a linear programming problem. So in standard form, we change these inequalities of each constraint into equations. And because for the first constraint, labor hours, we are talking of having an inequality of less than or equal to a type. And so that means whatever is on the left is slightly less than whatever is on the right. Not necessarily slightly, but is actually less than what is on the right or equal to. And so that means to make the left to be equal to change this inequality to equal sign, I therefore must add some quantity on the left-hand side. And that's what I'll call as S1. Similarly, for this second one, the second constraint on machine hours, the left-hand side is also less than the right-hand side. So to convert the inequality to equal, I must add some quantity on the left, which I'll call now the S2 or slack 2. And then finally, this one also I'll add slack 3. That will be the amount of the quantity. This will be slack 4. But then when you look at the last constraint about the directive of the bit tree, it is greater than. So the left is actually more than what is on the right. And therefore, for this inequality to change to equality, I must subtract a particular quantity. This now must be a surplus S5 so that then equality can hold. And so what happens now to the objective function is that the objective function now I must also integrate in. It will still be maximization as Z equals to, but then it will now be equal to 60x1 plus 80x2. And then now all these other quantities, they are also variables that have been introduced. They must now also be captured in the objective function. However, they are captured now with 0 coefficients. And the reason is because they do not contribute to the profit or to the maximum sales of this objective function. They have no profit and therefore have no effect on the objective function. That's why we have to capture them with 0 coefficients, all of them from 0 plus 0 S1 plus 0 S2 plus 0 S3 all the way to plus 0 S5. And so you have said the constraints, you have said subject to. This one is 3x1 plus 5x2 plus S1 equals to 900. And this is 5x1 plus 4x2 plus S2 equals to 1200. And this is 25x1 plus 18x2 plus S3 equals to 4500. And this is x1 plus x2 plus S4 equals to 200. And this is x2 minus S5 equals to 40. And then our negative constraints now, all of them, x1, x2, S1, S2, S3, S4, and S5. Each one of them is greater or equal to 0. Each one of them is greater or equal to 0. So all of them are non-negative. And so that's how we express a linear programming model into standard form. Now, once we've been able to express in standard form, it is now easy for us to calculate the slack and the surpluses associated with each of the constraints. And so we now pick, like, for example, if I want to calculate the slack surplus associated with the labor hours as the constraint, remember we only calculate the slack and surpluses at optimum point of the solution. And so at optimal solution, we have reported that the optimal solution of the above problem is obtained at x1 equals to 50 and x2 is equals to 150. So we only calculate at optimal. Once you have met the optimum point, how has each constraint performed? What is the performance of the constraint at optimum? And therefore, what then is remaining as a spare capacity of the underutilized or of fulfillment? So we calculate the slack and surplus at optimum point of the linear programming problem. And so when you look at the first constraint on labor hours, if I want to calculate S1, we have said that 3x1 plus 5x2 plus S1 equals to 900. And so if I'm substituting at optimum point, I'm getting S1 is 50 plus X2 is 150, then plus S1 is equals to 900. If I make S1 the subject, I'm able to get S1 as 0. To mean this is a constraint that is actually binding, because at optimum point, all the labor hours have been utilized and there is no spare hour remaining. So all the hours have been utilized fully. And so such a constraint must pass through the optimum point. Then when I look at the second constraint, and if I want to know the slack associated with it, I'll be looking at 5x1 plus 4x2 plus S2, which is said is equal to 1200. Again, at optimum, I'm talking of 550 into 50 plus 4 into 150 plus S2 is equals 1200. And so when I calculate this, I'm getting S2 to be equivalent to 350. And so that this means this is also a slack of 350. Now means that at optimum point, this particular constraint is not fully utilized. We still have 350 machine hours as spare that are underutilized. They are not used. And so that means the machine is actually idle for 350 hours at that optimum point of the solution. So 350 hours are spare time. The machine hours are just idle. So probably this could be important if these machines are hired, maybe per hour. You may want to consider all these 350 hours that you are paying for the machine, and the other machine is not in use during that time. And so if we continue again, even with the glass material, 25x1 plus 18x2 plus S3 equals to 4500, and substitute x1 and x2, we end up with S3 being equal to 550. That's the size of the material that is underutilized or not utilized at all at optimum. And so the coating material, we get S4 here. For the coating material, we get S4 as 0. Again, this is binding. Remember, we said the constraints that have 0 slacks are actually called binding constraints. The ministry directive, which talks of x1 minus x2 minus S5 equal to 40, and you have said x2 is 150, so minus S5 is equals to 40. So you find that S5 is actually 110. So this is a surplus. This is a surplus variable, because the means directive only requires that plant to have 40 energy saving bulbs, but then what that plant produces is 150. So it meets the requirement and actually surpasses by 110. This is an overfulfillment. It surpasses the target. And so, and by this 110. So this is a surplus. So we have, this is a surplus, while the rest are, all the rest are slacks. But then we have said that the labor hours and the coating material are said to be binding constraints. Are said to be binding constraints. Are said to be binding constraints. Coating material has that constraint x1 plus x2 plus s4 equals to 200. So those are binding constraints, only two binding constraints. And so if we plot all these constraints on a graph, we'll find that the constraint representing the coating material and the constraint representing the labor hours intersect. And where they intersect, that point is actually 5150, and it's actually the optimum point. It's actually the optimum point of this linear programming problem. So that's how we identify binding constraints. So binding constraints are easy to identify upon calculating the slacks associated with each constraint. And calculating the constraint, the slacks and the surpluses, we require to express the linear programming problem in standard form. Now we look at next the concept of sensitivity analysis, which will now drive us into computing shadow prices associated with also constraints. Shadow prices are actually binding constraints. We only calculate shadow prices for binding constraints. So, but before we mention what shadow price is, we define sensitivity analysis. And we are defining sensitivity analysis just as a further analysis upon getting the optimal solution of a linear programming problem. We always ask ourselves some questions whether there is a way in which we can modify the parameters or the assumptions of the linear programming problem or the formulated model so that we can get maybe a better solution. If it's a linear programming model of maximization kind, whose objective is maximization, you want to see whether the objective function can be made better in terms of increasing, or if it is a minimization objective function, we want to see if it can be made even further minimal. And so sensitivity analysis is just a post-optimal analysis upon getting the optimal solution and the optimum point of a linear programming. Any analysis that goes in to try to assess the extent to which the changes in the model parameters or assumption affect the optimal solution, and that process is actually sensitivity analysis. And so what could be the activities or some of the modifications you can do a linear programming problem that actually consists of sensitivity analysis? So some of the activities that actually constitute sensitivity analysis could be maybe changing the right-hand side of the constraint. If I've said x1 plus x2 is equals to, for example, 2 is greater or equal to 2, what happens if I change the right-hand side to 3 or to 4 or to 10, or I make it even smaller? How does that affect the optimal solution or the behavior of my optimal solution of the model itself? That's a sensitivity analysis. It's asking what if I do this. So whenever you're asking what if I modify this, I do this to the problem, then we are carrying out sensitivity analysis. What if we change the cost coefficients? Now, the cost coefficients, these are usually the coefficients of the objective function. Like for the previous example, 60x1 plus 80x2. So what if we change the 60 to, let's say, 70, and we change the 80 to, let's say, 75? How is the objective, how is the optimal solution affected? The changes in the constraint coefficients is also a part of modification. It can also be addition of a new variable or constraint altogether. You may realize there are two maybe variables only, and you want to include another one, a third, so that you're talking of three decision variables. Or you may want to add another constraint. Maybe the resource constraint are not sufficient. You want to add in other conditions or restrictions. You may want to delete a variable in the entire. If there are many variables involved, let's say 3, 4, you may want to delete one. How does it affect the optimal solution? Or you may want to delete even as a constraint also in the formulation. So all these constitute sensitivity analysis. Whenever you're doing all this, you are doing to assess the extent to which changes in the model. So these are model parameters or assumptions. How do they affect the optimal solutions? Whenever you're making such changes, you're actually doing sensitivity analysis. This comes after you have already solved the linear programming model and gotten your optimal solution and the optimum point. And through those modifications, through this sensitivity analysis, we now get what we call a shadow price of a constraint. A shadow price of a constraint. Now, a shadow price of a constraint is simply the difference between the optimal value of the objective function and the value of the objective function evaluated when the right-hand side of the constraint is increased by 1 unit. What I mean is that if we carry out sensitivity analysis on the right-hand side of the constraint, and in this case, we are looking at the binding constraints only, the constraints passing through the optimal point. And so if, for example, in the previous example, we identified two binding constraints. So we had the coating material X1, X2, was that, and then we had this. So this, let me use this one. So these were the two binding constraints. We had the coating material, and we also had the labor hours. So these were the binding constraints. And so if we want to calculate the shadow price, then we try to modify the right-hand side of these constraints. For example, if I pick these labor hours and say, what happens to the optimal solution if I change that constraint to 3x1 plus 5x2, now less than or equal to, let's say, 901 and not 900. So that I've changed now the labor hours. The change of cost is 1 unit, increased by 1 unit. So that 1 hour increase, how will it affect our optimal solution? Remember, we got our optimum point to be x150 and x2 150. And so if we substitute in the objective function, it gives us a value. But suppose now we modify this, do we still have the same optimal solution? Or it changes? If it changes, by how much? Is it higher, smaller? And so that change in the objective function from the original to now the new optimal solution, when we have now modified the right-hand side of a binding constraint by 1 unit, is what we now call the shadow price associated with that constraint. In some context, depending on the problem, it can be a shadow price of a constraint can be treated as the maximum price that the management is willing to pay for an extra unit of a given limited resource. So let's have a simple example involving just two resource constraints, which of course are now binding constraints, and see how we can be able to calculate the shadow price associated with each one of them. So we have two machines that are used to produce two products. And this narrative is actually summarized here. So there are two products, product 1 and product 2. And each product has to go through these two machines for them to be ready. So you can see product one, a unit of product one requires two hours processing time in machine one and 1 hour processing time in machine two. A unit of product two requires 1 hour processing time in machine one and 2 hour processing time in machine two. And then you have, on a daily basis, machine one is available for 8 hours only, because that's a maximum. And on a daily basis, machine two is available for 7 hours only. We have been told that a single unit of product one fetches a profit of 300 shillings for this particular company. And then a unit of product two fetches a profit of 240. And so this is a linear programming problem. We are asked to do what? To formulate a linear programming model for this and use a graphical method to find the optimal solution. And then calculate the shadow price for each machine. Then based on the shadow price, we also respond to the rest of those questions. Now you can see there are only two resource constraints. One associated with machine one and another one associated with machine two. And so it's not having so many constraints like the previous example. And so you only have these two resource constraints and two non-negative constraints, and then the objective function. And this case again is an objective function, which is maximization kind. So we'll formulate just as usual, maximize, if you have let the number of units for product one to be X1 and for product two to be X2, shall be maximizing 300X1 plus 240X2. And this is subject to the first constraint now be 2X1 plus X2 less or equal to 8. And the second one will be X1 plus 2X2 less or equal to 7. And so the non-negative constraints, we are talking, of course, X1 greater or equal to 0 and X2 greater or equal to 0. So we graph this, and after graphing them, we find the optimum point. And so when you do that, we shall be just getting the optimal solution for the first quiz, and we are able to get the optimal solution. So this is the model, the linear programming problem. And so when we graph, we are getting this as a feasibility region or the feasible region. And so if you consider all these corner points, we are able to get that the optimal point is actually this particular point here. And that point is actually having a 0.32. That's a 0.32 that will actually be optimal. And so if we now try to get the cells from these units, as you're saying, we get now maximum cells for the two products. For if we have three units of product one and 2 units of product two, and so they give us a maximum sales of about 1,380 if the units of cost are actually in shillings. So that's what we get if we do that. Now, this solution, this point can also be obtained without necessarily even graphing, because you realize there are only 2 resource constraints involved for machine 1 and for machine 2. So we can just solve 2x1 plus x less than or equal to 8, and then x1 plus 2x2 equal to 7, simultaneously as well. Just solving simultaneously, either using elimination, substitution, or matrix method, we should be able to get that particular point. And so that's the advantage when we are graphing. When you have 2 constraints, it's easy to solve a set of simultaneous equations when there are 2, when the set is 2. But when there are 3 or more, solving 3 or 4 equations simultaneously sometimes is tedious. That's why we discourage trying to use the analytical approaches. We only go for graphical. So we have 1380. This one, you have not done any sensitivity analysis. Just getting the optimal solution using graphical method, because you have two decision variables involved. So we are getting the optimal solution here as 1380. Now we are asked to calculate the shadow price for each machine. So we have to calculate the shadow price for machine 1 and for machine 2. Remember, those two constraints are binding. If you wish, you can find the slacks associated with each of these two machines at optimum point. For instance, 2x1 plus x2 plus s1 is equals to 8. No, x1 is 3 and x2 is 2. You can see is 8 plus s1 is equals to 8. S1 is 0. That's why you're saying that these two constraints are binding. And you have even checked the first one. It's actually binding at that optimal point. So let's see. For us to do that, we have now to just modify. You have to increase, because you're now doing the sensitivity analysis if you want to get the shadow price for machine 1. So machine 1, the right-hand side of the constraint is 8. So I need to change this 8 to, let's say 9, increase by 9, one value or 1 unit, so that it's 9. So that I now talk of 2x1 plus x2 is less or equal to 9, and x1 plus 2x2 less or equal to 7. Then I leave machine 2 constraint intact. And then I'll try to determine the optimal solution and the optimum point, and see how the optimal solution now changes. So that will help me now compute the shadow price for machine 1. So this is how now the linear programming model for when we are computing the shadow price for machine 1 will appear. So I've only altered the right-hand side of machine 1. Remember, we are doing sensitivity analysis on the right-hand side of machine 1 if you want to get shadow prices. So you realize that now if I solve these two simultaneously, my solutions now changes. The optimal point is now 11/3 and 5/3. This is where it is. The feasible region appears this way. These are now, if you investigate and evaluate those corner points, you find that the optimum point is now going to be this particular point. A point slightly lower than the other one, which was the original one was 3.2. This one has now dropped slightly. And it's because you can see this particular line, which was passing through 8 and 4, has now shifted to the right. It's actually parallel to this, because the two lines have the same gradient, but it has shifted, and so that's why it's changing now the new optimum point to that particular point. And so if I substitute now this point in the objective function, I now get a new optimal solution that I'm coding it at ZB, calling this point B now the new B. The original one was A, and it's giving me now 1,500 shillings as a profit, compared to the original one, which was 1380. So sensitivity analysis has caused the optimal solution to increase. And this has increased by altering the right-hand side of the constraint for machine 1 by 1 unit. So how do I then now calculate the shadow price? We have defined shadow price as simply the change in the optimal solution. So the shadow price would now be given by the new optimal solution minus the original optimal solution before sensitivity analysis, divided by the change in the right-hand side of that constraint that we are determining shadow price. So the new optimal solution is 1,500. The original one was 1,380. And we have changed the right-hand side of the machine 1 constraint from 8 to 9. So that difference is 1. Remember, the denominator is in hours, the numerator is in shillings. So we are getting this quotient being in shillings per hour, and we are getting 120 shillings per hour. Now, what this means to the manager or to the company involved is that for each hour increase, so that means, remember, the machines were available. Machine 1 was only available for 8 hours. But you have said if you hire it for an extra hour so that it serves the company for 9 hours, the extra hour is actually bringing in 120 shillings as profit. That for each hour increase, machine 1 brings in 120 shillings more profit. And so that is what actually means. And this could be information that could be useful for the management of that plant or that company to see whether this is a decision they can actually venture or try out. Now, we also need now to calculate the shadow price for machine. So the shadow price for machine 1 you have found is actually 120 shillings per hour. We also want to get the shadow price for machine 2 and see how much machine 2 is able to fetch as extra profit for every hour increase. Now, when you go to machine 2, we actually do the same process like what we have done in computing for machine 1. Only that in this case now, the right-hand side of the constraint for machine 2, we now increase it by 1. So we increase 7 by 1 to 8, and then maintain machine 1 as originally was, and then try to plot and determine the optimum point in the usual way. So when you do that, when you do the graphing for machine 2, we have now the formulated linear programming model appearing as you can see, 300x1 plus 240x2. The objective function remaining intact. Machine 1 constraint now remaining intact, but machine 2 constraint now we can change the 7 to 8. And so we check, and when we plot, the new optimum point is now 0.8 over 3, 8 over 3, or rather 2.667, 2.67. So this is the new optimum point. And when we substitute now this point in the objective function, we are now getting an optimal solution of 1,440. And this is actually now the new profit fetched when we carry out, when we modify the right-hand side of that second constraint by 1 unit. This is again slightly an improvement from the original optimal solution of the linear programming problem. And so if we want now to compute again the shadow price associated with machine 2, it is the solution it has given us when we have modified the right-hand side, 1440, minus the original solution, which is 1380, divided by the change in the right-hand side of this constraint, the change that we have done to this constraint, which is 1 unit, 8 minus 7, and you get 60 shillings per hour. And so what this means is that for each hour increase, or for each hour that we hire machine 2, it's able to fetch 60 shillings as profit for this particular, as profit for the company. And so now then the last thing I've mentioned under that I've said is that, and I think I've already emphasized here as a remark, that only binding constraints have shadow prices. So we only calculate the shadow prices for a constraint that is binding. But now there's 2 more questions based on shadow prices. Once you have computed the shadow prices, you have found machine 2 is actually 60 per hour. Remember, we now have a question here, say, based on these shadow prices, if we can increase the capacity of both machines, which machine should receive priority? We can see very clearly that if we increase machine 1, it will be able to bring in a profit of 120 shillings for every hour if we improve it by 1 hour extra. For machine 2, for 1 hour extra, it will be able to bring in 60 shillings per hour. And so the two are good, but given a choice, we shall go for machine 1, be given more priority because it fetches more profit for every extra hour compared to machine 2. And then should we increase the availability of machine 1 at an additional cost of 100 shillings per hour? What about machine 2? Now again, this is reasoning. So if we want to hire for every hour at 100 shillings, you can see for machine 1, if we still hire it 100 shillings, it will still be giving us some profit of 20 shillings for every hour. So it means we shall still be making some business, some good business. And so for machine 1, yes, this is okay. We can venture into that. But what about machine 2? Machine 2 is a big no, because it's only fetching for extra hours 60 shillings per hour. And so if we are hiring at 100, then of course the company will be making a loss. And so it's a big no for machine 2, but a big yes for machine 1. And so that's the logic of shadow prices and how to be able to help you. I'm sure now this definition makes some sense of shadow price. The maximum price the management is willing to pay for an extra unit of a given limited resource. So I think that definition now makes some sense up to that stage. And so that's the concept. That's how we do further analysis of linear programming problems. Thank you.